Okay, I think you can hear me now. All right. So thank you for the introduction, and I'm excited to take everybody home right now. So last presentation of the day, I'm the last thing standing between you and that big keg of beer. However, I know UIUC facilities, they won't have it ready till exactly 5:15. So as long as I don't go till then, you'll be all right. But I'm excited to present, as we just talked about, some of the sponsors of my research with one industry partner in particular, Bill Moorhead of Tramco LLC. So big thank you to him for sponsoring. I'll have the acknowledgments at the end too. Today, I'm going to talk about an alternative to under tie pads and a little bit about some other proposed uses for asphalt in the both wood tie and concrete tie world. So I'm going to jump right in. I'm going to start off quite basic because I'm not sure if everyone's familiar with asphalt, or it may be 10, 20, 30, 40, 100 years for some of you since your last class in undergrad where you talked about asphalt. So that's okay. I didn't look at anybody in particular when I said 100 years, by the way. So I'm gonna first just cover what is asphalt. Asphalt's basically when you extract petroleum, you distill all the high value stuff out. That's the stuff that fuels your jets, cars, and trains, of course. And then you're left with the heavy crude residue, and we use that to make asphalt mixtures. That's the asphalt binder right there. And we basically mix that with mineral aggregates to make asphalt mixtures. Currently, asphalt mixtures surface about 94% of the roads in the US, and that same statistic holds up for Illinois. Most states are over 90% asphalt surface. And the reason being, it's cheap relatively compared to Portland cement concrete. Generally, we do okay on the carbon footprint. It's very recyclable. It's something that we're working on making more sustainable for highways as well. And finally, it generally performs pretty well. So what do we use asphalt for? Of course, highways, as I just mentioned. Roofing shingles are another big application. And finally, there's been some research done by Professor Jerry Rose on asphalt underlayment, quite a large amount of research over the last 50 years and a lot of application as well, both in the US and abroad. So asphalt has been used in the rail industry before. It's not totally new to propose it, but we think that this application might have some promise as well. So that's what I'm going to talk about today. So under tie pads, right? Most of us are familiar with why we use under tie pads. Of course, preserving the ballast, vibration reduction, track stability, and in general, we try to reduce the maintenance requirement and extend the life of those ties. However, under tie pads are pretty expensive. I think we can all agree on that. They generally cost more than we would like to pay. So asphalt's a pretty low cost alternative. It's also generally sustainable. Here's what we propose as rubberized asphalt concrete. So that's moving faster than I wanted to, but that's okay. Basically, what we do here is we wanted to propose an asphalt mix that we feel will perform just as well as an under tie pad at a fraction of the cost. So we wanted to lower the cost by at least 50%. And the idea is to place this mix of what we call RAC, rubberized asphalt concrete. Basically, this is, first we take mineral aggregate and rubber. And again, that's ground tire rubber. You heard a little bit about that in the one of the under tie pad talks earlier. We also use ground tire rubber that increases the sustainability. And by the way, we're using more ground tire rubber here than is typically used in highway mixes that use a dry method of addition, which is what we use, basically where we mix aggregate and rubber together. Then we add a modified binder. That modification increases the performance life of the binder. And we mix it together. So we produce what looks like a loose asphalt mixture there. And we compact it on top of a tie, right? These are all images from our lab. And basically the idea here is, again, we want to produce something low cost. Asphalt's very low in cost compared to the components of UTPs. Aggregates are nearly free. And the tire rubber comes, again, from recycled ground tires. So not too cheap at all. And basically, we can produce this pad compacted on top of a concrete or a wood tie in our lab. For the purposes of today's study, we studied concrete, but we believe the application's agnostic to the type of tie, so it could be suitable for wood as well. I think in general, you'll see in the next slide, we tried a couple of different type of mixes. So cold mix asphalt was one thing we tried. Still a work in progress. We're not sure how that's going to pan out. As you can see, cold mix, the advantage is it's super workable at room temperature. You can work it without heating it up. That's my student touching it with just his finger. Cold mix is generally easy to work with, and it's chemically modified. It's an emulsion, the binder, so it's able to be used without heating it up. But so far, we've seen that it generally wasn't too promising in the first attempt, and we want to consider further modifications before we continue down that road. So instead, we want this traditional hot mix asphalt. Hot mix asphalt, typically you heat everything up, the aggregates and the binder up to about 150 degrees. That allows our rubber to absorb the binder really nicely and create a nice elastic network within our mix. And it allows us to also create slabs that when they cool down are pretty high in stiffness and seem pretty promising for initial evaluation. So what kind of mixes did we look at? We created 4 RAC specimens because we essentially want to make this a material that we can engineer to meet the requirements of any track bed. So we wanted to try out a few different mixes and look for what's the optimum for a specific application. So as you can see, we have a high asphalt, high rubber mix, mix number 1. Mix number 2 was high asphalt, but no rubber. Mix 3 was low asphalt, medium rubber, and mix 4 was low asphalt, no rubber. So kind of what we go from mix 1 to mix 4 is expecting to go from lower stiffness to higher stiffness, right? So now let's talk about what we did for testing. Basically, we examined 2 ballast plates. You heard earlier today about the GBP, right? So the GBP, as we know, has some flaws, so we wanted to check out a more realistic ballast plate too. We actually got one of the old plates that Marcus used in his research, and that's basically cured ARIMA aggregate gradation, and that's epoxied together. And we actually tested here in our lab. You can see that's the realistic ballast plate with the UTP alternative and concrete on top of it. And then in the leftmost picture is our GBP testing. So why did we run both if we had the realistic ballast? Well, the thing about our testing frame is that in general, it's hard to pick up all the local stresses and strains. It picks up bulk stresses and strains, right? So it's a lot harder to test with the realistic ballast, but we are going to look at some pressure sensors in the future to kind of try to look at that, as well as just some larger full tie testing schemes. My philosophy, and hopefully Bill agrees, is that in general, we feel that the best way to do it is test at the full tie scale, right? So that's something we're thinking about for the future of how to test it in the most realistic way possible. Why try to just do in the lab realistic when you can do something that's realistic to what we see in the field? So we did do the realistic ballast plate testing, and what we saw, first of all, this is the procedure just for kind of making the plate. I took this from one of the Rail Tech papers. Again, thank you to these guys for sharing that plate with us. That's also what we talked about earlier today with regard to GBP alternative. And again, it's not uniform like the GBP. It's not perfectly symmetrical. You probably won't get the same repeatability lab to lab, but it uses realistic ballast particles and ARIMA gradation to simulate the action of the ballast plate on the pad, right? So we ran quick 30K cycles just to see, we figured if this ballast, this realistic ballast is damaging the specimen, it would happen pretty early on. We'd see some sign of damage. And really, we didn't see any visible damage or anything concerning in the stress strain response, although again, it's not easy to measure the stress strain response because this is more about local pressures than global pressures. But we did see some keying action, which we actually consider a positive, right? The ballast locking into the pad to prevent any kind of movement and directly transfer loads from the tie. So we kind of felt that's actually a positive aspect, that the pad is a little bit flexible and the ballast does key in just a little bit and create some indentions. Those also do disappear over time. Asphalt's a viscoelastic material, so it recovers over time. So when there's no loading, those start to recover as well. Of course, this was 3 Hertz continuous loading, so didn't have time for that during the test. So we also ran the GBP bedding modulus because we wanted to get a feel where we were, especially compared to the targets out there in the literature. So static bedding modulus, I think a lot of you are pretty familiar with how that's calculated. Basically, you want the slope of that line, right? The load versus displacement line. This was based on EN standard, the procedure. So we went ahead and picked track category 3 as our target. I don't think it would have mattered too much which one we picked, but we selected there, track category 3. Here's a list of desirable ARIMA bedding modulus from their literature. And typically, we're targeting values up in this first upper right-hand corner. Typically looking at reducing maintenance, that's our goal. So we were kind of targeting the higher end of the values for our bedding modulus. For open track, pretty much any in that range. We were trying to be higher than even what we were talking about for freight rail, right? That's our goal here. So what do our results look like? Well, first of all, as I mentioned, asphalt's viscoelastic, right? So what does that mean? That means that the behavior of asphalt is dependent on loading rate, temperature, and also that the material has a memory, right? So what you see here is that actually the displacement increases slightly with every cycle. But what you'll notice when you start running in the thousands and tens and hundreds of thousands of cycles is that basically levels off at a pretty small displacement for us. What you do see here is that for 4 mixes, we kind of had 4 different moduli, right? And again, they're not perfectly consistent because of the viscoelastic nature of the material. But what you can basically see is they start getting stiffer and stiffer. That slope starts increasing a little bit. May be hard to see from there. So here are the numbers for comparison. First of all, what was our goal? Basically, we wanted to fall in between, 0.5, basically higher than 0.5 newtons per millimeter squared, as you saw in those proposed ARIMA bedding modulus minimums. So we wanted to fall at least there, with the ideal range about twice as high as that or more. So 0.35 to 0.6 newtons per millimeter squared. Probably around 0.35 is basically what we could consider our optimum bedding modulus for this purpose. Now, the great thing is about this mix is this isn't just a product and we have to say, well, it depends how you measure it. If the bedding modulus, if you measure it this way, the bedding modulus is this. If you measure it that way, it's this. We can't really change what's in our product. We just got to find the best testing method, or we just got to find the optimum formulation to tweak it a little bit. Actually, we can completely control the bedding modulus through properties of the mix. So that's the great thing, is this could be tuned to any application you want, right? So starting up at the top, you'll see that the high asphalt content and high rubber content generally leads to the lowest bedding modulus, right? So that may be appropriate for some light rail and things like that. And as you basically decrease rubber content, you lose some of the elasticity, you replace that with mineral aggregate, you essentially start bringing up your modulus pretty quick. And as you decrease your asphalt content, again, you have less asphalt. The asphalt's what makes the pad soft and flexible. So you start to see that the modulus goes up as well. Basically to the point where you're low asphalt, 0 rubber, you've got probably a modulus that's a little too high. But the stiffer you want to go, all you have to do is engineer the properties of your mix. That's the great thing about RAC, and that's really why we propose that this could be a great technology, because we could custom make it to any track bed that needs it, basically, or any tie, right? Just over here, you can see kind of the mix 1 fell in the acceptable range, 2 and 3 kind of right where we wanted to be, and then 4 maybe a little bit high. 0.81 seemed quite high compared to that 0.15 we were targeting, right? So basically, at the end of the day, we kind of see we do want some rubber. We want to add that elasticity. We want the pad to have some resilience, and maybe we want to look at kind of the intermediate levels of rubber and binder compared to what we were doing here. Now let's talk about fatigue results. We ran at, actually that should say 3 hertz, sorry about that, 3 hertz, 270K cycles. And basically we saw almost the same performance for all mixes except mix number 2. If you remember what mix number 2 was, it was high asphalt content and no rubber. But basically when we used rubber or reduced asphalt content, we saw almost the same performance and just about 1.5 millimeters deformation. You might say that's huge for an under tie pad, but I may have not said this earlier. Ours is almost 1 inch thick, right? So this is a very thick pad. It's not those 7 millimeter, 10 millimeter pads. This is almost 1 inch thick. So we're talking about 25 millimeters, maybe 1 millimeter, 1.5 deformation. So because we're closer to 25 millimeters, in the 20 to 25 range, right? Then we measured the bedding modulus before and after for mix 4. Unfortunately, we didn't do this for all mixes, but we imagine it's pretty much the same because you can see the deformation is almost the same, the pattern, at least for those 1, 3, and 4. And basically, it's almost unchanged, just a reduction of 0.81 to 0.78 after 270,000 cycles. So not much of a concern that there's any degradation of the pad, right? So essentially, that's what we've got so far. We're very excited about this idea because we think that this could be something that changes how we protect our ties and protect our ballast, right? Just get a touch on a few of the other applications for asphalt and kind of where our group sees the track bed going. Underlayment and overlayment. Again, Professor Jerry Rose has done so much work on this area in his career. He's really an encyclopedia of knowledge on these applications, and this could really help improve a lot of our tracks, especially with the new mechanistic empirical framework that Riley and Marcus have been talking about in their presentations. That mechanistic empirical framework, if we include asphalt overlayment and underlayment, especially underlayment in that, we do have a lot of years of data. That could be something that really, really improves the quality of our tracks. Second thing is the proposed life extension of wood ties based on the presentation of Bill Moorhead and Jerry Rose prior that you all saw earlier this afternoon. And essentially, our kind of vision is that you got an asphalt-based UTP on the bottom of the tie, you've got an asphalt coating on the top, and maybe you've got asphalt underlayment in the track bed. We see that as a track that potentially will never fail. That could be a perpetual track bed that, that's the level we feel this could be at. It's really something that, because of the viscoelastic property of asphalt, because of its damping effects, it can absorb those heavy loads and dissipate vibration, prevent damage, and just, if not make it perpetual, at least reduce maintenance by magnitudes we're talking. So I really think this is the future, and that's at least my biased belief towards asphalt, but I really do feel this is something very interesting. Just to get into the conclusions, again, RAC can be engineered to meet bedding modulus requirements pretty much for anywhere where you'd want to put a UTP, right? So we're not focused on, oh, we're good for these kind of tracks or this class. We can put it anywhere because we can engineer the properties. So again, that's what I think is really special about this material. Fatigue testing, again, minimal degradation after 270K cycles. In the future, we're going to do 3 million cycles once we've optimized the mix type, 3 Hertz. If you do the math, 3 million cycles at 3 Hertz is about a 12-day test. So we want to make sure we have the best mix in there before we do it. And finally, once we're proven in a large scale, simulated track bed, preliminary field studies, we believe this could be scaled up as serve as a low-cost alternative to UTPs. With that, I just want to acknowledge again Bill Moorhead for all his generous support of this research and sponsoring this work. It's been fantastic working with him. Professor Jerry Rose, all of his guidance and advice has just been so appreciated. Again, he's just a wealth of knowledge. Anybody who wants to learn more about asphalt, please, you should probably talk to him at dinner before you talk to me. He's got all the good information about its applications in the rail industry. Thank you to everybody at Rail Tech, especially Riley, Arthur, and Marcus, helping us out with the GBP, providing the realistic ballast and, just giving guidance throughout the project, especially as, I navigate this world that's kind of new to me, having a background in pavements. And then thanks, of course, to my grad student, Baba Kasadi, for, all of his efforts on experimental testing and analysis. So if you saw anything you liked in the presentation, these are all, these are the people responsible. I just did what I could, but you gotta thank all of these people too. And with that, I'm happy to take any questions. Thank you very much. Marcus. Yeah, great question. That's a focus of our. Oh, sorry. Yeah, he said, what about delamination? This is almost an inch thick, so there's a potential that it could get picked off, with the loading. It's a really good point, and it's something we're thinking about right now. Luckily, because asphalt's been so ubiquitously used in the highway industry, there are a couple of existing materials and ways to bond asphalt to other layers, because we've been bonding asphalt to concrete for 50, 60, 70, I'm not exactly sure the number, but quite a long time, a long number of years in the highways industry. So we're just thinking about the best way to do that right now. But yes, there are, right now, we would be concerned with that if we just put asphalt on the bottom of the tie, especially if it was a cold mix. But we think that we can add some adhesive, some kinds of tack or other adhesives to the bottom that would improve that delamination resistance. Yeah, back there. Yeah, not yet. And the contact area is a little tricky because this material has quite a texture. So I think the traditional contact area evaluation may not be appropriate for this material because asphalt's got a texture, right? It's not so flat and uniform at the surface. But it's something we're thinking about in the future. We haven't done that evaluation yet. Back there and then in front. So I think you right there in the blue shirt. Yeah. Good question. So that's the guy who knows about highways. Are you talking about the ballast aggregate or the aggregate in our mix? In our mix. So good question. For us, the angularity is a little less of a concern because this is actually based on finer fractions of aggregate. We're not using, because it's only an inch thick pad, right? So we're not using 1 inch aggregates, right? So a little bit less concerning for us than when you have those large crushed stones in a highway mix. And we're not really concerned about rutting at all because how much can you deform at an inch thick, right? So we're not really concerned about rutting with this mix. And that's actually why we're able to up the binder content and up the rubber content beyond what's done in the field. So it's not too much of a concern, but angularity of aggregates, of course, important just so you get good interlock within the mix. But generally we're kind of creating new gradations, right? We're not focused on highway gradations, so not as concerning. And then, yeah, just in front, you had a question. Good question. I think this was kind of based on the aggregates that we had. So again, typically you want to go at least 3-4 times thicker than the largest aggregate size. So mostly based on the type of aggregate we have. But we're open to other thicknesses as well. I think since we're able to tailor the bedding modulus, we can, if we need to reduce the thickness, we can just tailor the right mix to still hit the right bedding modulus benchmark. So I'm not too worried about that immediately, but yeah, it's something we're thinking about. Yeah, in the back.
Building on that question, did you look at the variability between samples of the same makeup /
Yeah, I think there was just one slide in here. I went through it quick. Yeah, so just between one replicate to the second. I think this was actually on the same specimen, but 2 bedding modulus measurements, at different times. So you see the repeatability there is quite good. Between samples of the same makeup, I would say probably it'll be a little off of there, but yeah, that's something we've got to check out too. But we haven't specifically looked into that yet. But again, you see the trend kind of follows how we'd expect. So I don't think you'd see a significant deviation from that for, a larger range of specimens. But yeah, that's something like before publication we're planning to look at. Yeah, another question here. Yeah, to be determined. So that's kind of the next phase of research actually is how do we make this thing happen, right? How do we scale this, translate it to the field? And that's really going to come from finding the right partner, to be honest. That's not something we can do as a university researcher. And I don't think Bill has that capability yet, although I never underestimate him. So, but we're looking for somebody, to partner with definitely who's interested in that. So, yeah, over here. Yeah, good question. I would say that would be something that would probably affect, variability specimen to specimen. So that may be something we haven't looked into that yet because actually, basically there's so much variability in asphalt itself just from, crude oil source to crude oil source and things like that. So then when you get into like regrinding, we're talking really casting that net wide. So I'd be a little hesitant to do that, but it's something we'd be willing to try. Yeah, back there. Compared to the under tie pads on the market? Yeah, I mean, cost essentially. So this would be probably less than 50% the cost of a typical under tie pad. I mean, asphalt's just so cheap comparatively, right? We buy it by the ton in highways. So asphalt, and this is on the more expensive side of asphalt mixes because it's got higher amount of binder, but still, I mean, it would just be huge cost saving compared to a conventional under tie pad. Yeah. Other questions? Yeah.
I had a little bit of history seeing what BN at the time and maybe some other railroads did with this material supporting the ballast. Is that still done unrelated? But is that still done on the railroad? I think it's when you have bad compaction areas like Panhandle.
Yeah.
Mexico, areas like that. How did that work out for the railroad?
A lot of places it worked out great. There's some places where we didn't put the track on it soon enough. It got basically some rain and it washed underneath. Jerry Rose, Dr. Rose, you speak on it. I mean, you gave me the Bible. Dr. Rose gave me the Bible of the Southern Transcon where all of the pavement is. And I gave it to Chris Swanson he's on our construction team, just to let you know. That's where it resides, but it's a treasured book. It's a wealth of history. I'll let Dr. Rose.
But you have to make sure that the drainage underneath the asphalt is proper. You've got positive drainage. Most of where I've noticed it hasn't worked, so to speak. If water saturates underneath, but the idea of the asphalt is to drain it off, so it has to be able to drain off. And if it's put down way too deep many times, then the water can't get out. It gradually soaks down and comes underneath. And if you get a real weak soil there, highly moisture content, very weak, its shear strength goes to nothing, and you've got a marshmallow down there. So it's not a bridge. It won't bridge. So
I remember many miles of that through areas in New Mexico when new construction was taking place. I just wonder how the history.
There were some stretches we paved and then we didn't put the track on soon enough. But otherwise, the track on that, we got that paved.
Yeah, great question. Any others? Any other questions?